evening to all. Let me clear that my voice is audible. Am I audible? Let me know that my voice is audible or not. Good evening to all. My voice is audible? Okay. So as you know, today's topic is grinding. So we are going to start grinding. Got it? So let's start today's topic, that is grinding. And I have shared the all PDF. I have shared all PDF from topic 1 to topic 35. I mean to topic 34. Okay, on your Telegram group, so that even I missed any topic, got it, even I missed to give you the PDF, so you can take that PDF, right? Right? Am I clear? So you can take that PDF. I have shared all the PDF. So today's topic is, my dear, grinding. So in grinding, basically, you know, in conventional process, and what do you mean by the conventional process, my dear? Conventional process means what? When the tool and workpiece are in contact. This is a conventional process now. When there is a workpiece and there is a tool, and when they are in contact, okay, and when the tool is going to apply a cutting force, then it comes under what? Conventional process. Am I right or wrong? So whenever the tool and workpiece comes in contact during cutting process, tool and workpiece, right, tool and workpiece. Whenever the tool and workpiece comes in the contact during cutting process, it's called as conventional process, conventional machining, right, conventional machining. Whenever the tool and workpiece comes in contact, and whenever there is no contact, without contact, okay, suppose that there is a workpiece and there is a tool, and they are not in contact, right, they are in not contact. Here you can see the tool and workpiece are not in contact, and the machining will be happen. That process is known as unconventional machining. Remember or not? Unconventional machining, and the example is, or other name is, non-traditional machining method like ECM, electrochemical machining, EDM, electric discharge machining, ultrasonic machining. Remember, water jet machining, abrasive jet machining. These are the examples. And in the conventional machining means whenever the tool and workpiece comes in a contact. My dear, please note, please focus on this statement. Please focus on this statement. Among the conventional machining process, the maximum specific power will be consumed in grinding. Yes, maximum specific power is what? I mean the power which is the energy which is going to be consumed to remove the per unit volume of material, right? So among the conventional machining process, maximum specific energy is consumed in grinding. Now you will ask, sir, why? Why maximum in grinding only? Why? The answer is very simple, my dear. This is what? This is grinding wheel. In front of you, you can see it is what, my dear? It is a grinding wheel. And in grinding wheel, there are infinite abrasive particle. Yes or no? There are infinite what? There are, sorry. There are infinite abrasive particle or not? Tell me. There are infinite abrasive particle, and these abrasive particle these abrasive particle have a angle. Okay, let me write down. There are infinite abrasive particle, and these abrasive particle have, actually there is what? There is infinite abrasive particle, right? There are infinite abrasive particle, abrasive, okay, abrasive particle. Sometime we call these abrasive particle as grit. Am I right or not? Sometime we call these abrasive particle as a grit. So grit will do a machining, or abrasive particle will do a machining. As you can see, abrasive particle, abrasive particle, abrasive particle, abrasive particle. Now the rake angle of these abrasive particle, okay, now I will talk about the rake angle. Rake angle of abrasive particle is what? Either it will be a negative, it will be a 0, and it will be a positive, right? It will be a positive. There are infinite abrasive particle, and the rake angle of the abrasive particle are what? Look, negative, 0 and positive. Am I clear or not? And you have studied, my dear, and you know already in theory of metal cutting, I told you, whenever the rake angle, whenever the rake angle become negative or 0, become negative and 0, tell me the required force and power consumption. In the wheel, there are infinite abrasive particle, there are infinite grit, which will do cutting process, and from infinite abrasive particle, the rake angle of the abrasive particle may be negative, may be positive, and may be 0. And you know, whenever the rake angle becomes negative and 0, okay, negative and 0, then the cutting force become increases, okay, the cutting force become increases, my dear, okay, the cutting force become increases, okay, cutting force what? Cutting force is increases. If cutting force increases, my dear, then what happened to the power consumption? What happened to the power consumption? Power consumption is increases. And you know, whenever the rake angle is negative and 0, tell me the required cutting velocity. Whenever the rake angle is negative and 0, tell me the required cutting velocity. Required cutting velocity. What will be the required cutting velocity? Whenever the rake angle is 0 or negative, what will be the required cutting velocity? What will be the required cutting velocity? Tell me. Whenever the rake angle is 0 or negative, tell me the required velocity. Tell me, beta, tell me the required velocity. I told you in theory of metal cutting, I explain each and everything, okay. Whenever the rake angle is what? Negative and 0, the required velocity is increases now. The required velocity, my dear, increases. Yes or no? Yes or no? Tell me. The required velocity is what? Increases. Yes or no? Tell me, my dear student. Am I clear? The required, no beta, whenever the cutting velocity, whenever the rake angle become negative and positive, you have to provide more cutting velocity. Then after the tool is going to penetrate into the workpiece, then the cutting will be happen. I told you in metal cutting class. That's why I told you the class is very important. That's why I explained about the rake angle, about the adverse effect of rake angle. If the rake angle is negative, 0, then the required velocity automatically increases. And you know, my dear, power consumption is what? Here, power consumption is what? You know, power is what? Cutting velocity and your cutting force and cutting velocity. If force is increases and velocity is increases, then power consumption is increases or not. And here, my dear, here in the theory of metal cutting, we discussed only one point, only one point tool, only one cutting edge. But there are more than one cutting edges, comes in a contact with the workpiece, So automatically power consumption increases very much. Am I clear? More velocity, more FC required, power consumption required more. Yes, Shiv Kumar Ahirwar, correct. So, am I clear, my dear? If you take the power consumption for one particle, automatically here you can see the power consumption will increases, but there are lot of grit which comes in a contact with the workpiece, so automatically the required power increases very high. That's why here the specific energy in conventional process is what? Is very high. Among the conventional process, specific energy in grinding is what? Very high. Am I clear, my dear student? Let me know, am I clear or not? Let me know, am I clear or not? Yes or no? Now tell me, am I clear? So it's a yes, it's a multi-point cutting tool. Grinding is what? Grinding is a multi-point cutting tool, because you can see here multiple grinding, here multiple points comes in a contact. So it is a grinding is what? Grinding multi-point cutting tool. Multi-point cutting tool, right? Grinding is what? Multi-point cutting tool. So am I clear? Now I will write again, or I will tell you one thing again. Why is high velocity desired in grinding? Why is high velocity required in grinding? My dear, high velocity is required in grinding because generally the rake angle in grinding wheel, the rake angle of abrasive particle in grinding wheel are low, means negative or zero. Okay, some are positive. Out of infinite abrasive particle, generally the rake angle are negative and zero, which are low. Okay, some are positive, but maximum rake angle are low. So to compensate the adverse effect of negative and zero rake angle, the required velocity will increases, my dear. The required velocity will increases. It is desired to offset the adverse effect of very high negative rake angle of the working grit. Okay, am I clear, my dear? Am I clear? So this is the thing. Now, this is a grinding wheel, as you can see. Okay, this is a grinding wheel, as you can see. You know, when the grinding wheel do cutting operation, suppose that the grinding wheel is rotating. Right? Now, suppose that when the grit comes in a contact with the workpiece, and suppose that when the chip is going to be produces, let's say chip is going to be produces. This is the chip. Can you tell me initially where the chip will go? Can you tell me initially where the chip will go? Can you tell me initially where the chip will be go? Let me tell you, this is what, let me tell you one by one. My dear, this is grit. First of all, the technical name is what? This is a grit, right? This is a grit. This is what? This is grit. This is grit. This is grit, right? This is grit. Clear? Now, the space between the grit is known as intergrit space. The space between the grit is known as intergrit space. Intergrit space. Intergrit space. The space between the grit is known as intergrit space. Initially, when the chip produces, then the chip will basically, okay, the chip will go in between the intergrit space like this. The chip will go in between the grit. When the wheel comes here, let's say the wheel will comes here. Let's say the wheel will comes here. This wheel will comes here, and this is an abrasive particle, my dear. Okay, this is the abrasive particle. Let's say this is the abrasive particle. Then what happened? The grit which comes here, okay, which initially which initially comes here, it will remove. It will remove. So this intergate space basically works as a pocket, okay, where the chip initially is stored, right? Also, this intergate space serve as a pocket for cutting fluid, right? Cutting fluid. Initially, the cutting fluid also goes there. Suppose that there is a cutting fluid, my dear. Okay, the cutting fluid is going to be there. Let's say this is what? This is a cutting fluid, right? This is a cutting fluid. So what is the advantage when the cutting fluid goes in between the space? What is the advantage when the cutting fluid goes in between the space? The advantage is, my dear, the chip will not stuck into the space. The chip can easily remove from the space because of the cutting fluid. And you know the advantage of cutting fluid, right? It will carry away the heat, right? It will not increase the amount of heat during the machining process. So this is a cutting fluid, okay, this is a cutting fluid, okay, and cutting fluid will okay, stored in the intergate space. And there is a many advantage of intergate space because of the cutting fluid. The chip will not stuck, okay, because of the cutting fluid, because of the cutting fluid, okay, because of the cutting fluid, the chip, because cutting fluid means what? It will act as a lubricant also. It will act as a lubricant also. So because of the cutting fluid, chips will not stuck in the intergate space, in the intergate space. Am I clear to all of you? Am I clear to all of you? Now my question is, my dear, what happen if the chip will stuck? What happen? What happen if the chip will stuck? Tell me. What happen if the chip will stuck? Then what happen? Can you tell me? What happen if the chip will stuck in the, okay, what happen if the chip will stuck? Tell me. What happen if the chip will stuck in between the space? My dear, if the chip will stuck in between the space, suppose that it will stuck, now it is stuck, Its chip is not removing, chip is not, leaving the space, chip is not leaving the intergate space. Every time the chip is what? Chip is going to be stored in between the space. Every time the chip is going to be stored in between the space. Every time the chip is going to be stored in between the space. See what happened? See what happened? The grit will not able to do a cutting process. See here, when the chip is not going to be removed, okay, evacuate the space, then every time what happens, the chip is storing into the space and the grit is not able to do a cutting operation. That wheel is known as what? Loaded wheel. That wheel is known as what? Loaded wheel, my dear. It is what? It is a loaded wheel. So loaded will not do any cutting. Loaded wheel will not do any cutting process. It will do only rubbing process. Okay. So this loading wheel will not do any cutting operation, not a cutting, cutting will not happen. Okay. Cutting not happen. Right. Cutting not happen. Only rubbing will happen. Only rubbing will happen. Okay. Am I clear? Pintu? Blunt tool, yeah, it may be a blunt tool, but initially what happened, the chip is going to be loaded in between the space, then the wheel called as a loaded wheel, and that loaded wheel will not do any cutting, it will do only rubbing. Am I clear to all of you? Am I clear to all of you? So these are some basic process. Okay, these are some basic process. Now, during cutting operation, there is a chance that the abrasive particle will also remove. During the cutting operation, there is a chance that the abrasive particle will also remove from the wheel. There will be a wear of wheel also there, right? So there is a ratio which is called a G ratio, my dear. There is a ratio which is called a G ratio. What is a G ratio? G ratio is basically defined as stock removal, stock, S-T-O-C-A, stock removed, okay, stock removed divided by, okay, stock removed in mm cube, divided by wheel wear, okay, wheel wear. Suppose the material is removed from the wheel. Suppose there is a wear of wheel also, okay, in mm cube. So G ratio is what? Material removed from the workpiece in mm cube divided by the wheel wear, the removed material from the wear in mm cube. My dear, if you want a good machining in grinding, if you want a good tool life of grinding, then the wear ratio should be minimum. Then automatically the G ratio will be increases. Automatically the G ratio will be what? Will be increases. Am I clear? The G ratio will be increases. So there is a question in GATE 2012 PI. There is a question in GATE 2012 GATE 2011 PI. Yes. What is the answer? Very less questions will be come in grinding chapter, right? Very less, very less. Grinding ratio is defined as volume of material, work material removed divided by volume of wear, right? Clear? It is simple, very simple. Now, this is a very important slide. This is a very important slide, my dear. This is a very important slide. Okay. Out of the grinding, whatever, I mean, this is a very important slide, okay. This is a very important topic and slide in grinding. I mean, in grinding wheel, basically, some parameters are written, and by that parameter, you can decide whether the wheel will be used for rough machining or whether the wheel will be used for finishing, right? Because generally, with the help of grinding, my dear, okay, with the help of grinding or from grinding wheel, suppose there is a grinding wheel, right? From grinding wheel, you want to do whether a rough machining, okay, right? Whether a rough machining, or you want to do whether a finishing, okay, finishing, okay. In rough machining, you know, large amount of material is going to be removed, okay, rough machining, large amount of material removed, and in finishing, you know, less amount of material is removed, right? Less amount of material is removed, right? So for that purpose, there will be a different grinding wheel. Or how can we select the grinding wheel? The question is, how can we select the grinding wheel so that it can do a rough machining, so that it can do a finishing operation? How can we select a grinding wheel so that it can remove large amount of material from the given workpiece, or how can we select that grinding wheel which can remove less amount of material, okay, from the workpiece? So to understand this, we have to understand the parameter. We have to understand the parameter which is required for grinding wheel. Now, my dear student, these are the parameter, right, by which you can decide by which you can decide you can decide the quality, you can know about the grinding wheel. By which parameter, by these parameter you can know about the grinding wheel. Am I clear? Am I clear? Now let me explain this. This is not for our purpose. This is prefix and suffix. This is not for our purpose. The only parameter is this A36, L5 or V. They can be vary, but what is the significance of this parameter? Let's try to understand. The first parameter, my dear, the first parameter which comes in the grinding wheel, it is a letter basically. It is what? It is a letter. This letter, what this letter tells us? What this letter tells us? Okay, if the letter is written, then it tells about the abrasive particle. It tells about the nature of abrasive particle. Nature means which type of abrasive particle you are using. Generally, the abrasive particle which we use, okay, generally here the abrasive particle which we use is either Al2O3, aluminum oxide, or is it may be a silicon carbide. It may be silicon carbide. These are very famous abrasive particle. Okay, these are very famous abrasive particle, and generally we prefer these type of abrasive particle. You can use the diamond also, but generally we use Al2O3 or silicon carbide. My dear, if let's say at the first place A is written, then the type of abrasive particle is what? Aluminum oxide. Suppose that in a first place instead of A, okay, suppose at the first place instead of A, if the C is written, then it means the abrasive particle which we are using is what? Silicon carbide. Am I clear? The first parameter is crystal clear to you? Tell me yes or no. The first parameter is crystal clear to you? Tell me yes or no, my dear. This is a very, very important slide. Tell me, is that clear? Is that clear, my dear? Now, the second parameter. The second parameter basically a number is there. A second parameter is a number is there. What the second parameter explain to us? Second parameter explains that the size of the grain. Yes, the size of the grit or grain. Okay, the size of the grit or the grain. Please pay attention. Please pay attention. This is basically a size. Okay, this is basically a size. Look, this is a table. Here the number is written, my dear. Here the number is written. Let's comes here. Look, let's comes. At the second place a number is written, right? Now, numbers tell the grit size or grain size. How the grit is small, okay, how a grit is large, got it? How much grit is small and how much grit is large. Simple. So see, as in the chorus row, as in a chorus column, the number is what? 10, 12, 11, 20, 24. In medium, 30, 36, 46, 54, 60. Fine, 70, 80, 90, 100, 120, 150, 180. Very fine. 220, 240, 280, 320, 400, 500, 600. What does it mean? It means that in the second place, as the number is increases, the grit become finer. My dear, the grit become finer. Am I clear or not? Tell me, am I clear or not? As the number is increases at the second place, it means that grit become finer. Yes or no? Yes or no? Are tell me, Baba, yes or no? So, my dear student, you know, the fine grit will be used in which case? Where fine grit has a tendency, right? Fine grit will be used in a finished grinding wheel, right? In a finished grinding wheel, in a finished grinding wheel. Because fine grit means the grit size is small. If the grit size is small, then material removal capacity is less. Okay, material removal capacity capacity is what? Material removal capacity is less, right? Material removal capacity is what? Less if the grid size is fine. And in finishing case, we want to remove the less amount of material, right? Here in rough machining, we prefer large grid. We prefer large grid. Okay, we prefer large grid, right? We prefer large grid because large grid has a, okay, material removal capacity is high. Material removal capacity is what? High, is high. Yes or no? Am I clear or not? So I hope you understand. Okay, I hope you understand. In a rough machining, the size of grit is large. In finished grinding wheel, the size of grit is what? Is small. Right? That is the advantage of this parameter. That is the advantage of this parameter. So I hope the second place is clear. I hope the second parameter is clear. Now, my dear, the third parameter. Third parameter, again a letter comes. Again a letter comes. Third parameter tells us about the grade. Okay, third parameter tells us about the grade. See, third parameter tells us about the grade. Grade, basically a number. My dear, what do you mean by the grade? I will tell you. Basically grade. Let's come here. Grade comes here. Look, at the third place you have seen a letter is there. What is the meaning of the grade? The meaning of the grade is how much strongly the abrasive particle attach with the wheel. How much strongly the abrasive particle, sir, a larger grit means chorus. Yes, Narendra, larger grit means chorus. Okay, larger grit means what? Chorus. Large size means what? Chorus. And number will be less, right? Yes, what I am telling? At the third place tells us about the grade. Grade means a letter. Grade means how much strongly the abrasive particle is attached to the grinding wheel. Am I clear? Am I clear? How much strongly the abrasive particle is attached to the grinding wheel. Am I clear? Yes or no? First of all, tell me. First of all, okay, suppose that your teeth is what? Your teeth is abrasive particle. Your gum is what? Your gum is what? Your grinding wheel, right? A wheel where the grit is attached. So how much strongly your gums are holding your teeth? That is a grade. That is a grade, right? That is a grade. How much strongly your gums holding your teeth? Your teeth are abrasive particle and your gums are what? Is a wheel, bonding material. Your gums are what? Bonding material. So how much strongly your gums are holding the teeth? Similarly, how much strongly the wheel is holding the abrasive particle? My dear, if the letter will go from capital L to A, means the grade decreases, means the wheel is soft, means the holding power of wheel to hold the abrasive particle is less. When you go from capital L to Z, it means the grade is increases. It means the holding power of bond is increases. Okay, it strongly hold the abrasive particle. Am I clear or not? First of all, tell me. Am I clear or not? First of all, tell me. The third parameter is clear. The third parameter is clear. The third parameter is clear. Now the fourth parameter. Fourth parameter, my dear, fourth parameter means structure. Fourth parameter is structure. Structure means porosity. Structure means intergate space, right? Structure means what? Let me explain you structure. Structure means the intergate space, that the space. Structure. What structure tells us? Structure tells us intergate space. Structure tells us intergate space. Intergate space. Okay, intergate space. How much there is a space in between the abrasive particle? How much there is a space in between the abrasive particle? Okay, if you say that the intergate space or structure is what? Porous. porous, porous, okay, porous. The structure is porous, means the space is large. And if you say the intergrid space is what? Dense, dense, okay, dense, it means what? It means what? It means that the space in between the abrasive particle is less, is very less, right, is very less. Am I clear or not? Am I clear or not? Yes or no? Tell me. So, fourth, that is a structure. A structure will tell you the intergrid space, right, the intergrid space. Let me show you. Let's say there is a number, at the place of a structure a number is written 5. Look, look, this is a table for the structure. This is a table for a structure. Look, dense to open. Look, dense to open. Look, as the number is increases 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, etc. It means dense to open. As the number is increases, it means the structure is going to become from dense to open. Means the space in between the grid particle is increases. Am I clear? The space in between the grid particle is what? The space in between the grid particle is increases as the number is increases. This is the meaning, my dear. This is the meaning. Is that clear? The fourth place is clear. Tell me everybody. 1, 2, 3, 4. Right now I have explained 4 parameter. Are these 4 parameter are clear to you? Are these 4 parameter are clear to you? Are these 4 parameter clear to you? Are these 4 parameters clear to you? Now the last parameter is what? Fifth parameter, that is a bonding type. I mean bonding material. Bonding material. Yes. The last parameter, sir, in third, sir, where loose holding grade, use AB. You cannot say loose holding. Strength is sufficient, but it has a little bit less strength compared to capital L. If you compare, let's say if you compare A with L, with respect to L, here the holding power, here the bonding strength, here the bond strength is less. Okay, if you say that the letter is C, in third parameter, if you say the letter is C with respect to L, means the bonding strength is little bit less. Okay, which bonding strength? Which hold the grid. Or if you compare C with respect to A, here the bonding strength to hold the abrasive particle, is little bit more compared to A. Always we compare, my dear. Okay, am I clear? Prasad, always we compare. Okay, always we compare. It doesn't mean the strength is very less. If you compare to each other, then we can say about the strength. Now the last parameter is what? That is the fifth parameter. It tells you about the bonding type. Okay, about the bonding type. I mean which bond you are using to hold the abrasive particle. Suppose that if you writing here V, so the bonding material is vitrified. If you writing S, then the bonding material is silicate. If you writing R, the bonding material is rubber. If you are writing, let's say if you are writing B, then the bonding material is resinoid. If you are writing E, then the bonding material is shellac. If you are writing O, then the bonding material is oxychloride. Right, oxychloride. Am I clear? So these are the 5 parameters which are very important in terms of the grinding. Okay, so only this is a possibility. Only in the, from this topic, the question will be come into your GATE exam. Like what? Like this question. Like see this question. Okay, suppose that if that question comes in your GATE exam, suppose that, and if I mark this, then I will ask in the exam, what this parameter indicate? Tell me, what this parameter indicate? You know this is prefix and suffix, so this is not a concern for us. If I mark this parameter in GATE, a question will become, and he will be marked any one of the parameter, and he will ask in the GATE exam, what is the meaning of this parameter? Tell me, what is the meaning? What is the meaning? Grid size, very good. That type of question will become, right, grid size. It tells about the grid size. It tells about the grid size, right? It tells about the grid size, my dear, right? It tells about the grid size. So that type of questions will be comes, right? That type of questions will be come into your exam. I mean, there are lot of there are lot of other topics are there, but these are theoretical, and you feel become bored if I explain this thing. So I'm not teaching. So I'm not going to explain these topics. Got it? Only there is a chance that yes, there is a chance that a question will become only from this topic. Now it's time to introduce me next topic, that is a shaper, planer and slaughter. I mean, there are a lot of things. There are a lot of things in grinding, my dear. There are a lot of things in grinding, but for a gate point of view, it is sufficient for you people, right? For a gate point of view, it is sufficient you people. Got it? It is sufficient for you people. Now, the next one is your shaper, planer, slaughter, and it's the last topic of the machine tool. It's the last topic of the machine tool. Tomorrow I will start the metrology. Got it? Tomorrow I will start the metrology. Then after the metrology, I will start what? I will start the material science. Right? I will start the material science. So let's start here. Look, here in a shaper, planer, slaughter, please see. In a shaper, planer, slaughter, please see. Look please. In a shaper, planer and slaughter. Here, what is a shaper? You know. A tool is there, or I will draw also, right? I will draw the figure also. I will draw the figure. Look, there is a workpiece. There is a workpiece. This is a workpiece. This is a workpiece. Now, in the shaper, planer, slaughter, what happened? A tool is there, right? A tool is there. Let's say I am talking about the shaper. Okay, let's say I am talking about the shaper. Tool is there. Let's say tool. Now, this tool will do a cutting operation. How? This tool will, this is the length of the workpiece. This is what? Length of the workpiece. This is what? Width of the workpiece. Let's say it is width of the workpiece. This is the length of the workpiece. Now, my dear, tool will become along the length of the workpiece. Okay. So, when the tool will become in forward direction, it's called a cutting stroke. It's called a cutting stroke. So, this is what, my dear? This is a cutting stroke. Okay, this is what? This is a cutting stroke. Clear? This is what? This is a cutting stroke. Cutting stroke. Am I clear? This is what? This is a cutting stroke. Okay, there are a lot of formula in shaper, planer, slaughter. But if you understand the process now, then there is no need to learn the formula. I mean, already there are a lot of formula in mechanical engineering. Lot of formulas are there. How many formula you will remember? So it is better that to understand the process. If you understand the process, then you will solve the question without using any formula. Without using any formula, you will solve the question, right? And there is a less chance. There is a less chance that in shaper, planer, slaughter the question will become. Then unnecessary. Why you are learning the formula? I'm not getting. Okay. Why are you making your life so complicated? So when the tools go in a forward direction along the length of the workpiece, then it is known as a cutting stroke. Suppose that here the tool reached. After the cutting, here the tool reached. Now what happened? The tool will move in upward direction. The tool will move in upward direction. Let's say the tool is moved in upward direction, and it will again go to its initial position along the same path, right? It will again go to its initial position again along the same path. So this is known as return stroke. This is known as what? Return stroke, my dear. Right? This is known as return stroke. Return stroke. Right? Return stroke. So in a one single stroke, there will be a two stroke. In a one single stroke, there will be a two stroke. Which one? Cutting stroke and return stroke. Once the tool will reach to its initial position, then the tool will move. Then the tool will move along the width. Okay, my dear. Then the tool will move along the width. Are you getting my point? Then the tool will move along the width and tool will reach there. Now again, okay, this is the feed along the width. This is what? This is a feed along width. Okay, feed along width. After complete stroke. After one complete stroke, and in one complete stroke, there is a cutting stroke, then along the same path, there is a return stroke. Once the tool will reach its initial position, then the tool will move along the width, right? Again, the tool will do the same cutting stroke, right? Cutting stroke. Once the tool will reach here, then it will do a return stroke, right? Once it reaches to its initial position, again the tool will move along the width of the workpiece. Now it will do what? It will do a cutting stroke. Along the same line, the tool will go to its initial position and it is a return stroke. Am I clear? So what happened? The machining will take place. Okay, this is a path of the tool. Along which machining will take place. Am I clear? Along the path of that, the machining will take place. Am I clear, my dear? This is the machining. Okay, this is the path of the machining. Now, for better clarification, I will draw the top view. Also. Let's say it is a top view. Right, it is a top view. Suppose that you are seeing this scenario from the top. Right, from the top. So, from the top, my dear, it means it is what? It is a width. It is a width of the tool. Oh, sorry, width of the workpiece. This is the width of the workpiece, and this is what? The length of the workpiece. Now, initially, let's say the tool is there. Okay, initially the tool is there. Right. Now the tool will move along the workpiece and it will do a cutting operation. Right. Suppose that along that path, the tool will move. Along that path, this is the tool. Now the tool will move along the workpiece and it will do a cutting operation. Right. It will do a cutting operation. So once the tool will reach there, at that position. So when the tool will go in this direction, it is known as what? Cutting stroke. Okay, it is known as what? Cutting stroke. Cutting stroke, my dear. Cutting stroke. Okay, cutting stroke. Now, when the tool will go to its initial position along the same path, it is what? It is a return stroke. Return stroke. Yes or no? It is clear. Now, once the return stroke, after the return stroke means tool will reach at its initial position. Now the tool will move along the width of the workpiece. Now the tool will reach there. Right. Now once the tool will reach this position, then it will do what? Again the cutting stroke. So this is the cutting stroke. Right. This is the cutting stroke. So this is the cutting stroke, my dear. Okay. This is the cutting stroke. Now the tool will reach there. Okay. Tool will reach there. Now after that, it will return to its initial position. On the same path. Am I clear to all of you? Is the shaper planar sort? Is the shaper is clear? In shaper, tool is moved. The only difference is that in shaper, tool is moved. In planar, work table will move. In shaper, tool is moved. And in planar, what happened? Work table is moved. Am I clear? Yes or no? Tell me. Am I clear? Yes or no? Tell me. Am I clear, my dear? Yes or no? Arey Baba, tell me. In shaper, only tool will do the cutting. Okay, only tool will move. In planar, what happened? The work table will move. In the same manner, the work table will be moved. In a planar, in shaper, tool will be moved. Got it? And what about the slaughter? Okay, this is the shaper. And what about the slaughter? In slaughter, basically what happened? We use a hydraulic machine where we can hold a workpiece on a work table. We hold the workpiece, okay, in a work table, and suppose that this is a top view. Suppose that I am drawing a top view. Suppose that I am drawing a top view, right? Suppose that I am drawing a top view, okay. In that workpiece, basically what we try, we are going to make a slot. We are going to make a slot. So that's why this machine is known as what? Slaughter. A tool will move up and down, up and down, up and down, up and down, and a slot will be cut, okay, and the slot will be produced in this workpiece. So that machine is known as what? Slaughter, right? So there is a cutting stroke, return stroke, cutting stroke, return stroke, cutting stroke, return stroke, simple. So in the same manner, in a slaughter we can do machining. Now, about the formula, my dear, look, what is about the formula? I mean, there will be a cutting speed, a formula, lot of formulas are there. Look, lot of formulas are there. If it's your wish whether you want to learn the formula or not. But I will not recommend to learn the formula. I will show you. Without using any formula, you will solve the question. Okay, without using any formula, you can solve the question. It's your wish whether you want to learn the formula or not. Okay, whether you want to learn the formula or not. So let me introduce a question so that you can understand that without using any formula, we can solve a question. Right? Right? So this is a question for you. Please read out carefully. Please read out carefully. Please read out carefully. Then I will solve the question. I am going to give you 2 minutes or 5 minutes, then after I will solve the question. Still, if you want to learn the formula, I will explain, don't worry. But what I am focusing, that why are you learning these formula? I mean, there is a very less probability that the question will be come from shaper, planar, slaughter. Very less probability. For that thing, why are you, okay, giving your extra effort? It is better that you give your extra effort in the important topics. Because in the important topics, there is a more probability that the question will be come. So tomorrow I will start the metrology. Look, what the question is saying. Question is saying, I am drawing a top view, right? Top view. This is a top view. A 600 mm and 30 mm. Are you trying or shall I solve the question? This is the width of the workpiece, that is 30 mm. Right, this is the width of the workpiece, that is 30 mm. And 600 mm, this is 600 mm. This is 600 mm. 600 mm. Is to be finished machine on a shaper. The plate has been fixed with the 600 mm length, 600 mm side along the tool travel, means the tool will be moved along the 600 mm. This is the top view I am drawing. Okay, let's say the tool is here. Let's say the tool is here because I have seen if the tool over travel at each end of the plate is 20 mm, means what? The distance from the workpiece and the tool is 20 mm here, right? And the distance from the workpiece, okay, distance from the workpiece and the tool again 20 mm here, right? 20 mm here. trying. Yes, I'm just explaining, I'm not doing anything. If the tool over travel at each end of the plate is 20 mm, average cutting speed is 8 meter per minute. Average cutting speed is 8 meter per minute. Okay. Feed rate is what? 0.3. Feed rate is 0.3 mm per stroke. Means cutting stroke, return stroke, then the tool will move along the width of the tool. Okay. Cutting stroke and return stroke, cutting stroke and return stroke, then the tool will move along the width of the workpiece. That feed is given. That feed is what? That is 0.3 mm per stroke. Per stroke. Am I clear? 0.3 mm per stroke. Right. And the ratio of the return time to cutting time. The ratio of the, beta, I am representing TR, return time, and I am representing TC, cutting time, is what? 1:3. 1:2. 1:2. Okay. You have to tell the total machining time. My dear, please try to understand. My dear, please try to understand. Okay. Please try to understand this question. I mean the question. Please try to understand. Look. This is a workpiece. Okay. Now. Now suppose that initially the tool is here. Initially the tool is here. Tool is 20 mm away. How much? 20 mm away. Right? 20 mm away. And once the cutting will happen, the tool will go 20 mm over travel. 20 mm over travel. And this is the length of the workpiece. That is what? That is 60. So during cutting stroke, please listen me carefully. Please listen me carefully. Okay, please listen me carefully. During cutting stroke, tool will travel that much distance, yes or no? Tool will travel that much distance. Okay. And after cutting, my dear, after cutting, tool will move again the return stroke, yes or no? Are tell me yes or no? Tell me. I explain you na. During cutting stroke, on the same path, tool will travel what? Tool will travel what? That much distance, means 640 in cutting stroke. After that, after the cutting will be happen, then tool will do a return stroke on the same path, means again it will move 640 mm. Then after that, the tool will move along the width. Okay, suppose that tool will reach here. Okay, again it will do a cutting stroke, my dear. Again it will do a cutting stroke. Okay, again it will do a cutting stroke. Okay, cutting stroke, and it will do a return stroke. Then again it will move along the width of the workpiece. It will do a again what? Cutting stroke. Again on the same path it will return. Again on the same path it will return to its initial position. Am I clear or not? Yes or no? Tell me yes or no? Tell me Baba, yes or no? So my dear, the cutting, okay, length, because you are not getting the concept, so I am writing each and every step for you people only. Length travel in cutting stroke. Length travel in cutting stroke. Okay. Length travel in cutting stroke. How much? 20 plus 20 plus 60, 640. 640 mm per stroke. In one stroke, okay, one stroke means what? I mean it is a mm per cutting, per stroke. So 640 mm length is going to be moved by the tool. Yes or no? Yes or no? Now I want to know the number of stroke. How many number of stroke will be there? How many number of stroke How can you find? In width of the workpiece is what? 100, right? Width of the workpiece is what? Sorry, width of the workpiece is what? Width of the workpiece is 30, right? This is the 30. This is a 30 mm. So how many stroke will be do in a width in along the 30 mm width? 30 divided by 0.3, 30 mm and 0.3 mm per stroke. So how many stroke will become? 100 stroke. Am I clear? My dear, in one stroke, basically there will be a two stroke. One stroke will be complete by the cutting stroke and the return stroke. Cutting stroke plus return stroke. Is that point is clear? Tell me. Is that point is clear? One stroke means cutting stroke along the same path. There will be a return stroke, then one stroke will be complete. Tell me yes or no. Tell me yes or no. Tell me yes or no. Now, I'm talking about only the cutting stroke in a one stroke only. I'm talking about the time taking in cutting stroke. Now, in one stroke, there will be a 640 mm length travel during cutting operation. Now there is a 100 stroke. So in every stroke, what should be the total cutting length? Total cutting length in 100 stroke. In 100 stroke, it will be what, my dear? It will be what? 640 into 100 mm. So it comes 64 meter, right? 64 meter. Now my dear, the cutting velocity is what? The cutting velocity is 8 meter per minute. Okay, average cutting speed. My dear, please try to understand. Okay, VC is a cutting velocity in cutting stroke, and during return stroke there will be a velocity VR, return velocity. There will be a velocity of the tool, there will be a return velocity. Yes or no? Yes or no, tell me. Cutting velocity and there will be a return velocity. Okay, there will be what? There will be a return velocity. Look, there will be a return velocity. Okay, yes or no? There will be a return velocity. Yes. So it is obvious, then in one stroke there the time taking by cutting stroke plus if you, for a cutting stroke, time will be taken by, like, let's say TC during cutting operation, and during return the time taken by the return time is TR. It makes a one stroke time. Right. Now, how much time taking in cutting stroke? In cutting stroke, that is what? 64 divided by 8. 64 divided by 8. So how much it will become? 8 minute. Right now, 8 meter per minute is a velocity 64. Right. Now, you know that the TR, one thing is given na, TR by TC. Return time divided by cutting time equal to, what? 1 by 2. So what will be the total return time? It will be TC into 1 by 2, and TC is what? 8 by 2 means 4. So the total time is what? TC plus TR means 8 plus 4 means 12 minutes. Let me know, is there any formula required? Let me know, is there any formula required? No, na? Is there any formula required? Yes or no? Is there any formula required? No, there is no formula required. Got it? So why don't waste your time. But still you want me, sir, please explain the formula, then I will. It's my duty. It's my duty. If you want to learn the formula, it's your wish. Okay. Cutting speed is what? Basically N. N is what? N is the number of stroke. And you know how can you find the number of stroke? How can you find the number of stroke? That is width of the workpiece. That is width of the workpiece divided by feed along the width. Okay. Okay. Feed along the width. So number of stroke. So how can you find the cutting velocity if you want? The number of stroke into L, that is cutting length into 1 plus M. M is what? M is the ratio basically. M is the ratio, that is the TR by TC, and it is always less than 1. Okay, it is always less than 1. Right, divide by 1000. Got it? So it is the one formula for cutting speed if you want to calculate. It is a number of stroke if you want to calculate. Time of one stroke. What is the time for one stroke? L. L is the cutting length into 1 plus M. M is the ratio of TR by TC. Divide by 1000 into V. That is what? Cutting velocity. It comes in minute. It comes in minute. Okay. Total time. Total time, that is the cutting length into 1 plus M. M is what? The ratio TR by TC. Divide by 1000. And it is a capital V. That is a cutting velocity, my dear. That is a cutting velocity, capital V, into what? Into NS. Okay. So it's up to your wish whether you want to learn the formula or not, but my recommendation, don't learn the formula, right? Because there is a less chance the question will be, there is a less chance that the question will be come from shaper, planer, slaughter, right? So that's it for today's class, and that's it for the machine tool. Tomorrow I am going to start metrology. Okay. So thank you. So just after the class I will share the notes. In fact, I will share the notes right now. In fact, I am going to share the notes right now. Now check your telegram. I have sent it. I have sent it the notes. Check your telegram. Right?